Hello everybody and welcome to the 18th lecture of MHM for 2780. Last week we talked about the overall heat transfer coefficient sorry, as well as cooling factor. We also solved an example together. Today we are going to speak about analysis of heat exchangers. Most probably, when you start working as a mechanical engineer specialized in heat transfer, you will face with a situation that you need to select a heat exchanger or to satisfy a specified temperature range or predict the outlet temperatures. When you are dealing with the first situation means that you need to select a heat exchanger to satisfy a specified temperature change. You need to use log mean temperature difference method. And why? Because you have all those temperatures. But while if you are dealing with the second scenario, which is predicting the outlet temperatures, there is another method called epsilon NTU, or effectiveness NTU. We are going to talk about it just like the effectiveness NTU. Just be familiar with those words. So you cannot actually pick the method that you want to analyze the heat exchanger. The situation and the condition of the project that you are dealing with will dictate basically which method you can use, but there are many situations that you can use both of them, and the answer that you receive from those two methods should be more or less the same in like a 2-3% variation. Okay, so it is important to first analyze the problem that you are dealing with, see what kind of information you need, what kind of information this question is asking you, and after that you can deal with it. Okay, here in this slide, I just summarize what I told you about when you are starting as engineer. You are dealing with two different methods, like for selecting log mean temperature difference, that we call it LMTD, and effectiveness epsilon NTU method or epsilon NTU method. Okay, let's besides that, there are some assumptions that we need to make. Let's start with making some assumptions, because we cannot model a real actual heat exchanger. Instead, we need to make some acceptable engineering assumptions to make it easier for ourselves, because sometimes adding extra detail or complexity to the question won't help us a lot. But as a like an engineer, most of the times you are not going to design heat exchanger, or you are not going to build it. Basically, based on the requirement of the project, you go and you buy it. It's a kind of like out of shelf. So there are different companies that they did all those calculations. They just come with a nice kind of like a software. If you want to pick from their product based on your condition, you go through their catalogs and you pick the heat exchanger that you think is the best for your company or for the place that you are working. But assumptions that I talked earlier, first is a steady state. acceptable engineering assumption when we are dealing with the heat exchanger. The second one is constant mass flow rates. The third one, okay, let me just like write it here. So let me open a page immediately after here and I just write those assumptions. So assumption one, I just like said that is steady state, steady flow. Second assumption is constant mass flow rate. Flow rates for both sides, like hot and cold. Constant fluid properties at inlet and outlet. We know that some of the flow properties, for example density or K or Cp, they change based on the temperature. And when you have a temperature at the inlet outlet, if you remember when we solved one example last week, we said that okay, we just read the properties of fluid at the average temperature of inlet and outlet for like, for example, if the cold water is coming at T cold in and goes out at T cold out, we are going to read the temperature of water at T average, which is T cold in plus T cold out divided by 2. So it's a good engineering assumption, but we didn't consider flow, the proper fluid property fluctuations based on temperature. The fourth assumption is kinetic and potential energy change. Potential energy change. We consider both of them to be negligible. Another assumption, specific heat of fluid should be considered constant. So no variation by temperature or pressure. 6.1 heat conduction along the tube considered negligible. So we neglect the conduction heat, axial conduction heat transfer. And the last assumption is that the outer surface of heat exchanger assumed to be perfectly insulated. Okay, now we have these 7 assumptions. Those assumptions are very good, acceptable engineering assumptions that will make our life much easier, because we can calculate what we need easier, faster, but at the same time they are not going to affect basically the accuracy of our calculations a lot compared to the real or actual situation. Now let's go back to the previous slide, because you know that I just like open this page to just write these assumptions. So considering all those assumptions from the first law of thermodynamics, we know that the rate of heat transfer from hot fluid needs to be equal to the rate of heat transfer to cold. So here you see that the heat transfer from cold fluid, C, we use C to show the cold, and hot for hot fluid, H here. So when we are saying the heat transfer should be the same, so it means that Q dot, let me just Q dot C here and Q dot H, they must be the same. Am I right? Or they are equal. M dot C, CPC, we call it C, like a capital CC, and M dot H, CPH, we call it capital CH. What are they? They are, we call it heat capacity rate. So inlet, hot fluid heat capacity rate, cold fluid heat capacity rate. If we put them into this, the first correlation, we can see that, for example, for Q dot C, we can replace M dot C, which is the mass flow rate of cold fluid, multiply by this specific heat of cold fluid. Together, we know that will make the heat capacity rate of cold fluid. So we replace it. So finally, we will have a very simple equation here. We do the same thing for the hot fluid, and again we are having a very simple equation. Besides that, we need to know that condensers and boilers are two common heat exchangers that widely used in industry, and they involve a phase change process. To add that to our analysis, we have another level of complexity. For example, if I go back to the previous slide, you can see that it was very simple. So the hot fluid comes with a temperature of hot inlet, loses some energy and goes out with a lower temperature than inlet, TH out. On the other hand, cold fluid comes in with a lower temperature, absorbs all that energy because we are neglecting the losses, and the cold water temperature increases and goes out. But in boiler and condensers, we said that they involve the phase change process. So phase change process, we know that during the phase change process, the temperature will stay the same. Why temperature stays the same? Because this HFG, or the rate of evaporation or condensation of the fluid, this Q dot needs to be absorbed by the cold fluid when we are talking about condensation or boiling. If I want to give you an example, if you remember, for example, here, just think about that. If we have saturated water, we know that the saturation temperature of water is 100, and here we will have saturated vapor. Again is 100 degrees. But what is happening in this process, it's a phase change process, okay? Because in order to this process, the phase change happens, you need energy. It's the same as that one, so you need to receive it from hot fluid. When you receive this temperature, so of course the hot fluid will lose temperature, and in condenser is vice versa. And finally, the rate of heat transfer in a heat exchanger can also be expressed as, you remember this U, we talked about it last week, so overall heat transfer coefficient, AS, you know what is that, and delta Tm is an appropriated or mean or average temperature difference between the two fluids that we are going to talk about it and see how we can calculate that delta Tm. Okay, now here we are going just to talk a little bit about the log mean temperature difference method here and how this appropriate form. So if I go back to the previous one, it's like LM here. I think we just like yeah. So now we are going to find this appropriate form of the average temperature difference between the two fluids. What we are going to speak about, we are just like, first we are going to find it for a parallel flow double pipe heat exchanger. As you can see in this figure, there is a double pipe heat exchanger. The configuration is parallel flow. Temperature difference between hot and cold fluids are, the inlet and outlet temperature are given, and we know that the temperature difference between hot and cold fluid is large at the inlet but exponentially decreases toward the outlet. By measuring all the temperature differences you see here, the delta T1, delta T2, we are going just like to talk it, and also making all the assumptions that I mentioned earlier for analysis of heat exchanger. We say that for differential section showed in this figure, we want to write the differential energy balance. Okay, so the differential energy balance for cold fluid is basically this one, and differential energy balance for hot fluid is this one. So delta T H, delta T C. It's just like it's a little bit of mathematical manipulation. And dH, d temperature hot minus the temperature cold. Just write it, and if you take all those steps shown here, you can find this correlation that we call it log mean temperature difference. But what is delta T1 and delta T2? Here we talked about parallel flow. So for parallel flow, delta T1 is T hot inlet minus T cold inlet. These two. The difference between these two temperatures. And delta T2 is the difference between these two temperatures. So what does it mean? It means that when I have another configuration, let's say my configuration is not like this, it's like this is the hot and this is the cold. It's not parallel. What I'm going to have, so it's T hot in is T cold out. This is T cold in and T hot out. So here for me, delta T1 will be T hot inlet minus T cold outlet, and delta T2 will be T hot out minus T cold in. So configuration can play a big role here for calculating the log mean temperature difference. Keeping in mind that when we said this one, delta T1 is equal to T hot inlet minus T cold inlet, and delta T2 is T hot outlet minus T cold outlet, is not always the same. So it depends on the configuration of the heat exchanger. Okay. But I don't think we need to speak more about it because it's quite clear. But if you go to figure sorry, I don't know what figure is like. Let me just first talk about something else, and after that we can go and when I find the figure number, I'm going to talk about it. Okay. So here you see that it's exactly the same thing that I was telling you about, how the different configuration can affect the temperature differences here. Delta T1 and delta T2, it's basically is the same as the situation that we dealt with here, but if it's not parallel and it's counterflow, so I talked about it, so basically is this situation that we talked. But let's say, what is counterflow heat exchangers? So it's basically the name is self-explanatory. So you see that counterflow, basically when the hot fluid and cold fluid they are running in two different or opposite directions. In the limiting case, as you see here, the cold fluid will be heated to the inlet temperature of the hot fluid. But we said that there is a big difference here. If you look and compare it with this one, you see that the out or outlet temperature of a cold fluid cannot be higher than the outlet temperature of hot fluid, whatever it is. So they can be close, but they can't be exactly the same or even be higher. But if you look at that the counterflow heat exchanger, you see that no, that's not the case. So T cold or outlet the cold fluid temperature at the outlet can be much higher than that of the hot fluid outlet temperature. Okay, so that's something that you need to keep in mind. But what we were talking about in both those cases, as you can see here, we were talking about just one pass. But what will happen if there are multiple passes? Will that affect? Of course that will affect. Now we are going to talk about that. So we talked about parallel counterflow, but that in industrial application is very rare or almost impossible to have just like a one pass. So in industrial applications we normally face with multi-passes, cross-flow heat exchangers, and for those heat exchangers we cannot develop any mathematical relationship for log mean temperature difference. So what we are supposed to do then? Any idea? So in this case we relate the equivalent temperature difference to the log mean temperature difference of the counterflow with the correction factor. Okay, so correction factors, if you go to your textbook, figure 1119, page 664, there are correction factors for common cross-flow, shell and tube heat exchangers with different configuration, and you can also read from the figure, so you can see it. We are going to show it as well. So in that case, what we are going to do is that we are going to somehow relate the log mean temperature difference of a multi-passes heat exchanger or shell and tube or whatever to one pass. In order to do that, we need to have a correction factor, which depends to geometry. Okay, so what is CF here? Single pass. So basically when we have a multi-pass cross flow, so we have a correction factor log mean temperature difference of one pass cross flow. Okay, there are as I told you on page 664 of your textbook, you see that there are some figures for correction factors like this, but you see that there is R, there is like P. So you need first, in order to be able to use these figures, you need to find R and P. So how you can find them? It's very easy. The correlation is like here, T2 minus T1, T1 minus T1, T1 minus T2, T2 minus T1. But what are they? What is small t? Sorry. So what are those T1, T2 that we see here? We can quickly just like check. If you go to that figures that I told you, you see that here is shown. So basically this is like the inlet temperature, outlet temperature, inlet temperature, outlet temperature. The same story. So it's completely clear in different situation or configuration. For example, here A, we are dealing with one shell pass and 2, 4, 6 or any multiplier of 2 tube passes. Okay, so we immediately go to the right hand side. We realize that okay, what is T1, what is T2, what is capital T1, what is capital T2. We just go to calculate it based on that number, and R, we can find the correction factor. When we have the correction factor, we go and calculate the log mean temperature difference for counterflow, and after that multiply it to the correction factor, and we have the log mean temperature difference for our multi passes heat exchanger. The same story with the different configuration. If we are having 2 shell passes, we just like go for first to the right hand side sorry, to understand what we are talking about. We find all those temperatures, and after that again, based on the R and the P number that we calculated, we will find the correction factor. There are other figures as well that you can find the correction factor for single pass cross flow with both fluid unmixed, and single pass cross flow with one fluid mixed and the other one unmixed. Okay, so those words means something when we are saying that the hot fluid, for example, is mixed, the other one is unmixed. You need to give attention to the detail, because the information that you are reading from those figures can play a critical role in accuracy of your final result. Basically, I think that's it from today. Tomorrow we are going to solve one example together and see how we can put this kind of like going to the table or figures and read those P, R, and after that finding the correction factor will work. Okay, thank you so much and enjoy the rest of your day.